Sean wants to go to the state fair and has $50 to spend. He intends to spend all of his money. The admission at the fair is $8, plus the price of the tickets for the rides is a whopping $1.50 each. Since we don't know the number of tickets he will purchase, we will use X to represent the number of tickets he will buy. Now, let's develop an equation to help Sean determine the maximum number of tickets he can purchase. In this phase of the video project, we're going to help you to reinforce your skills in working with equations. We'll see how real-world examples actually involve working with equations. Now, let's see about having some fun, fair equations. We know that Sean will have to pay an admission of $8 in total to get into the fair. We also know that he'll have to pay $1.50 per ticket. Since it's $1.50 per ticket, we will use T in this video to represent the number of tickets he will be purchasing. We also know that his total budget for the fair is $50 in all. One way to help Sean solve his dilemma is to simply have him to deduct all of his expenses from the total amount he has to spend. If you'll notice, we have the $8 admission coming off the $50 equaling $42. And then for each ticket he purchases, he simply deducts another $1.50 until he gets down to having no money. If he wanted to do it by paper and pencil, I think that would take a few minutes. $1.50 is continuously subtracted until there's no money left. If he continues the pattern for purchasing tickets at the rate of $1.50 each, he'll be out of money after purchasing possibly 28 tickets, you think? Let's see. Now, for an easier way to come to the same conclusion, let's work it with an equation. Let's verify whether or not that 28 we project for the number of tickets is correct. Since Sean has $50 to spend, this is how he'll spend it. $8 for admission, $1.50 per ticket, $1.50 T. Remember, the T represents the number of tickets for each ride. The $50 is the total budget. If we take $50 and set it equal to the admission plus the $1.50 we'll spend per ticket, we have what's called possibly an equivalent equation. Let's explore that. The coefficient on the variable T is the numerical factor when a term has a variable. An equation has different components, the coefficient being one of them. Another component of the equation is the constant term. The constant term is a term that has no variable factor, such as the $8 and the $50 parts of our equation. Now, to solve the first equation, we want to first isolate the variable. We begin by moving all terms, with the exception of the T, to the other side of the equal sign. If you'll notice, the $8 is the amount that's on the side of the equal sign with the $1.50 T. We want to isolate the T, therefore the 8 is made to move. We do that by virtue of inverse operations. Inverse operations are operations that undo one another. For example, the $8 is eliminated by combining it with a negative $8. And the law of balance causes us to do the same thing, combine the $50 with a negative $8. Also, combining $8 with a negative $8 is called opposites. Opposites are two numbers that are the same distance from zero on the number line. The sum of two opposites is 0. Hopefully you can see that the opposite of $8 is simply negative $8. Again, since we combine negative $8 on one side of the equal sign to isolate 150t, we must also use the rule of balance and do the same operation on the other side of the equal sign, causing us to use the negative $8 to be combined with the $50. The $42 equaling 150t will lead us into developing the idea and discussing rational numbers. Rational numbers are numbers that can be written as a ratio of two integers. Rational numbers in decimal form are terminating or repeating, such as 1.5, $8, or the number 50. Let's use this time also to discuss a few other algebra concepts, such as subtraction. The law of subtraction says if A equals B, then A minus C is equal to B minus C. We did the same thing with our equations. A would be the $50, C would be the $8, B would be our $1.50 T. Therefore, if $50 minus $8 can equal the 150 T, resulting from our original equation. The result of that would be the $42 equaling 150 T. To get the exact number of tickets that can be bought, we use what's called the rule of division. The rule of division is if A is equal to B and C is certainly not equal to 0, then A divided by C would equal B divided by C. And if you'll notice in the work, if you'll take $42 as A, again, $1.50 T would be our B. We would divide by C, our $1.50, and the law of balance would cause us to do the same thing on both sides of the equation, resulting in T equaling $28. T equaling $28 is what's called our solution. A solution is any value of values that make an equation true. In our case, we verified that Sean can indeed buy 28 tickets on a budget of $50 by having used the equation method, the equation solving method. Since we found our solution, with our solution, we can evaluate our equation to determine whether or not our solution is correct. To evaluate an equation is to evaluate an expression with variables by substituting a number for each variable. Our variable is T. If we take the $28 we solved for, substitute it back into the equation, giving us $50 is equal to $8 plus $1.50 times $28, you'll see we have resulting equal numbers, causing us to know that our solution is correct. We've had Sean to use a couple of ways to find the number of tickets he can purchase on his $50 budget. He's used the method of subtraction with paper and pencil. He's also used the method of equations. Now, since we're in the age of technology, Sean could whip out his trusty calculator and have that answer in no time. Let's see how that can be accomplished. In Y1, he can have entered his total budget. Y2, the amount that he's going to be spending, the admission amount, as well as the amount that he's going to be spending for tickets. If you'll notice in the graphing calculator, instead of T, we have to use X. If you'll list both parts of your equation and two separate Y equal menus and graph that equation, we can start with a zoom 6. You'll be able to see a decent picture of the graph. This is the graph, the diagonal line you must realize is the graph of one of the equations, and that's the graph of the y equals 8 plus 150x. Where is the y equals 50? To be able to see that, you must adjust your window. If you go into your window, we know that our y equals 50 is above the 10 we have from our zoom 6, we can simply multiply this times 7, changing our y max to 70, graph again, and get the graph of both lines. But we can't see the point of intersection. The point of intersection is where our solution occurs. So we're going to have to go back in and change our x max, multiply that. We know from previous projections that our solution is at 28. We'll simply multiply this one by 4 to increase it to 40. Graph again. And this time, we can see the point of intersection on the screen. We don't have to use the trace menu to be able to get to our point of intersection. We can use the graphing calculator to have it to generate the point of intersection for us using the intersection mode in the calc menu. Therefore, we'll go second, calculate, 5 for intersect. The calculator then asks you, is my cursor on the first curve? If your answer is yes, hit enter. The cursor will then move to the other curve. If the answer to the calculator's question is my cursor now on the second curve, hit enter. The calculator says, now give me a guess of where you think the point of intersection is. Move your cursor to a point, any point near the point of intersection, and hit enter. And the calculator will calculate the point of intersection for you, verifying the fact that Sean can purchase 28 tickets on a $50 budget. Our previous calculator manipulations lead us to discuss the concepts of equivalent equations. Equivalent equations are equations that have the same solution. For example, we can take what we put in y1, $50, and y2, the $8 plus 150x, and come to the solution of $28. If we would take the $28 substituted back into the equation, that would make the $8 plus 150x equal $50, creating what's called equivalent equations. Now, let's talk about order of operations. The graphing calculator always does math manipulations according to the order of operations. You know about order of operations also. Ever since you were in elementary school, I'm sure you've heard, please excuse my dear Aunt Sally. If you'll notice, when we took the $8 plus 150x or t, substituted the $28 back in, the operation of multiplication had to have been done first in order for the appropriate solution of $50 to be derived, meaning that multiplication must be done before addition or subtraction. Order of operations are these. You perform any operation or operations within the grouping symbols first, then you simplify any terms with exponents. After that, you multiply and divide in order from left to right. And lastly, you can add and or subtract in order from left to right. Now, since you've seen how Sean can have fun with equations in his everyday life, especially having fun with it at the fair, let's review the concepts we talked about, and then you'll have that same opportunity. We talked about the parts of equations, such as the coefficient on a number, the constant term in an equation, and rational numbers. We also talked about operations on equations that include inverse operations, opposites, subtraction, and division. We defined solution and evaluate, and we discussed equivalent equations and the order of operations. Now, your instructors will provide you with activities that will give you the same opportunity as Sean had. Please have big fun.